Salam, peace be upon you. My name is Muhammad Layiq Sadiqi, the father of Holophase. Part 43 Coarse Graining Declared Loss in Phi Pattern Readability. We began with one insight pattern is primary. Phi is circular comparability, the root permission for distinction. Only relations are public. Identity is invariance under lawful transformation. Persistence is certified survival through change. Interaction is joint constraint. Time is ordered transformation. No ex nihilo. Every appearance has provenance. The observer is a pattern within pattern reality. Measurement produces traces. Memory stabilizes them. Models compress structure. Prediction narrows lawful futures. Learning updates structure while preserving identity. Intervention alters coupling. Computation transforms patterns under rules. Information is constrained on possibility. Publicness makes knowledge shareable. Scale determines what becomes visible. Now we ask, how do we move between scales without pretending nothing was lost? The bridge between scales. In the previous part, we learned that scale determines what aspects of a pattern become visible. At one scale, we see fluctuations. At another scale, we see stable structure. At still another scale, we see entirely different organization. But this raises a practical question. How do we move from the fine description to the coarse description? How do we pass from billions of molecules to the smooth flow of a river? How do we pass from millions of people to economic trends? How do we pass from neural activity to thoughts? The tool that allows this transition is called coarse graining. Coarse graining is the method by which detailed descriptions are transformed into simpler ones. But the key insight of Phi pattern science is this. Coarse graining is not just simplification, it is lawful loss. A simple everyday example, the digital photograph. Think of a digital photograph. The original image has high resolution, millions of pixels, fine detail. We can see individual leaves on trees, the texture of skin, the grain of wood. Now we reduce the resolution. We average groups of pixels together. We create a smaller image, fewer pixels, less detail. What happened? We performed coarse graining. We deliberately lost detail. The new image preserves some structure, the overall shape, the major features, the composition. But it discards fine detail, the individual leaves, the skin texture, the wood grain. Is the new image wrong? No. It is a different representation at a different scale. It may be more useful for some purposes, faster to load, easier to see overall composition. But if we pretend we lost nothing, if we claim the coarse image contains all the detail of the original, we are deceiving ourselves and others. Coarse graining requires honesty about what was lost. The meaning of lawful loss. When we coarse grain a system, we discard some information. That loss is unavoidable. The world contains enormous detail. No model can capture every aspect of every interaction. But if the loss is declared uncontrolled, coarse graining becomes a powerful scientific tool. If the loss is hidden, the result becomes misleading. This is why coarse graining must always be treated as a transformation with declared loss. It preserves certain aspects of a pattern while discarding others. And this change in detail alters what becomes legible. The city map. Imagine trying to navigate a city. You could use a satellite image that shows every building, tree, and street sign. But such an image might be overwhelming. Instead, we use a city map. The map removes enormous amounts of detail. It discards the color of buildings, the texture of roads, the shape of windows, the movement of people. Yet the map preserves the structure we care about, roads and intersections. The map is a coarse-grained version of the city. The loss of detail is intentional. The simplification works because the discarded information is irrelevant to navigation. But if someone forgot that the map removed detail, they might mistakenly believe the map is the city. That confusion illustrates the central danger of coarse graining. Another example, the population average. Consider a population of people. We measure their heights. We have individual data, each person's exact height. This is fine scale information. Now we compute the average height. We produce a single number, the mean. What happened? We coarse grained. We discarded all individual variation, all the distribution of heights, all the outliers. We preserved only one statistic, the central tendency. The average is useful. It tells us something about the population, but it does not tell us everything. If we pretend the average captures all the information, if we say the population is 1.7 meters tall, as if everyone were that height, we are hiding the loss. Coarse graining requires declaring what was lost. What coarse graining does? Coarse graining performs several transformations simultaneously. It discards certain structures, it preserves selected invariants, it changes the regime of legibility, it introduces uncertainty, and sometimes it reveals patterns invisible at finer scales. These transformations allow scientists to analyze systems that would otherwise be impossible to understand. But the price is lost information. The weather example. Consider the atmosphere. At the smallest scale, air consists of trillions of molecules moving randomly. Tracking every molecule is impossible. Weather science therefore uses coarse graining. Instead of individual molecules, meteorologists describe temperature, pressure, wind speed. Each value represents the average behavior of billions of particles. The molecular detail is discarded. But the large-scale structure of the atmosphere becomes visible. Storm systems appear. Jet streams emerge. Climate patterns become legible. Coarse graining makes weather science possible. Yet, meteorologists know that the coarse description hides microscopic fluctuations. The loss is acknowledged. Why undeclared loss is dangerous. When coarse graining is performed without declaring what was lost, serious errors arise. Hidden loss can produce fake patterns. For example, a dataset may be averaged across time. The average appears stable, but the stability might simply be an artifact of smoothing. The underlying system could be wildly fluctuating. Similarly, a scientist might group data points into large categories. Patterns might appear in the categories that do not exist in the original data. The pattern is not discovered. It is created by the coarse graining. This leads to four major dangers. Fake laws appear when regularities are artifacts of averaging. Fake invariants appear when stability results from hidden aggregation. Fake emergence appears when patterns arise only because detail was discarded. Fake certainty appears when uncertainty from lost information is ignored. An example, the smooth signal. Imagine a signal that is random noise, no pattern at all. Now we smooth it. We average neighboring points. The smooth signal shows smooth curves, apparent trends. If we do not declare the smoothing, we might think we have discovered a pattern. We might publish a paper about the trend in the data. But the trend is an artifact. It was created by the coarse graining. Without declaring the loss, we have produced a fake pattern. What must be declared? A lawful coarse graining claim must declare what is lost, which structures are discarded, which details are removed. This is a loss inventory. What is preserved? Which invariants survive the transformation? Why the loss is acceptable for the target scope? For what purpose is this coarse-grained representation suitable? How uncertainty changes. Loss of detail introduces ambiguity. The model must acknowledge that. How replayability is affected. If others follow the same procedure, can they reproduce the result? What invariants survive? Which features of the pattern remain unchanged under coarse graining? Without these declarations, a coarse-grained representation is incomplete. It may be useful, but it is not yet a public pattern claim. An example, the census data. A national census collects data on every individual: age, income, education, occupation. This is fine-scale information. The Census Bureau publishes summaries: average income by region, age distribution by state, education levels by demographic group. These are coarse-grained representations. A responsible Census Bureau declares: what is lost? Individual privacy, local variation, outliers. What is preserved? Aggregate statistics, population trends, regional comparisons. Why loss is acceptable? To protect privacy while providing useful information for policy. How uncertainty changes. Sampling error, margin of error reported. How replayability is affected. Methods published, microdata available to researchers under controlled conditions. What invariants survive? Relationships between variables that hold at aggregate level. This is honest coarse graining. Coarse graining as transformation. Coarse graining is best understood as a transformation operator. If we denote the detailed description of a system as X and the coarse description as Cx, then coarse graining can be written symbolically as Cx. This operator converts the micro description into a macro description. The transformation discards detail but preserves certain features. For example, a list of billions of molecular velocities might be transformed into a single temperature value. The temperature is the coarse-grained variable. It summarizes enormous complexity, but it does not contain all the information of the original state. Multiplicity of microstates. When we coarse-grain a system, many microscopic states correspond to the same coarse description. Imagine describing a classroom simply by the number of students present. 20 students might be in the room, but there are countless ways those students could be arranged. Each arrangement is a different microstate, yet they all correspond to the same coarse description: 20 students. This multiplicity is crucial. It reveals that coarse graining hides many underlying possibilities. Entropy and coarse graining. The number of hidden microstates associated with a coarse description is what scientists call entropy. Entropy measures how many microscopic configurations correspond to the same macroscopic description. For example, a deck of cards shuffled randomly has high entropy because many arrangements produce the same coarse property, a shuffled deck. A perfectly ordered deck has low entropy because fewer microstates correspond to that condition. But entropy only makes sense once the coarse graining is defined. If we change how we group microstates into macro descriptions, the entropy changes. Therefore, entropy is always relative to a chosen coarse graining. Entropy without declared coarse graining is meaningless. The river again. Let us return to the river. At microscopic scale, we observe water molecules colliding randomly. At larger scale, we describe the river by flow velocity and pressure. The microscopic description contains enormous information. The coarse description compresses that information. Many molecular states produce the same flow velocity. The flow variable is therefore a coarse-grained property. Entropy measures how many molecular arrangements correspond to that flow. Coarse graining reveals structure. Interestingly, coarse graining can reveal patterns invisible at finer scales. When we zoom into a noisy signal, we may see chaotic fluctuations. When we average the signal across time, a smooth trend may appear. The trend was hidden by noise at the finer scale. Coarse graining removed the noise and revealed the underlying structure. But this revelation only works when the loss of detail is acknowledged. Otherwise, the smoothing might be mistaken for a genuine law. The crowd example. Imagine observing a crowded stadium. At the level of individual spectators, behavior seems chaotic. People move unpredictably. But if we observe the crowd from high above, patterns appear. Waves travel across the stadium. Groups synchronize chants. The coarse-grained view reveals collective behavior. Yet, the individuals still exist beneath the pattern. Coarse graining allows us to see the group dynamics without tracking every person. 18. The role of coarse graining in science. Nearly every scientific field relies on coarse graining. Physics uses it when describing gases and fluids. Biology uses it when describing populations rather than individual organisms. Economics uses it when describing markets rather than individual transactions. Sociology uses it when describing communities rather than personal interactions. Climate science uses it when describing global patterns rather than local weather. Coarse graining allows complex systems to become understandable, but its legitimacy depends on declared laws. 19. The coarse graining principle. We can now state the central principle of this part. Coarse graining is how Phi Pattern science moves across scales without pretending no information was lost. Declared loss is honesty. Hidden loss is smuggling. This principle ensures that simplified descriptions remain scientifically responsible. The rigor layer, the coarse graining gate. Because coarse graining is so powerful and so dangerous, pattern science introduces a specific gate. The coarse graining gate ensures that any transformation involving loss of detail is properly declared. This gate asks several questions. What exact procedure produced the coarse representation? What information was discarded? What invariants were preserved? How did uncertainty change? How does the transformation affect replayability? Is the loss justified for the intended purpose? If these questions cannot be answered, the coarse-grained claim is not legitimate. The coarse-graining gate requires loss inventory, what is discarded, preserved structure, what survives, loss justification, why acceptable, uncertainty change, how confidence changes, replayability impact, how reproduction is affected, surviving invariance, what remains unchanged. Additional gates. Several additional gates reinforce this discipline. The loss declaration gate ensures that discarded information is explicitly listed. The preservation invariation gate verifies that preserved structure is clearly identified. The uncertainty propagation gate ensures that the increase in uncertainty is accounted for. The replayability gate ensures that the transformation can be repeated by others. The entropy gate confirms that multiplicity of microstates is correctly interpreted and that coarse graining is declared. Together, these gates prevent coarse graining from creating misleading patterns. Firewalls against smuggling. Several firewalls protect the integrity of coarse graining. Firewall 1. No silent averaging or smoothing. Every coarse graining must be declared. Firewall 2. No hidden thresholding that discards inconvenient data. Selection must be justified. Firewall 3. No presenting coarse patterns as fundamental laws without acknowledging lost detail. Macro patterns depend on coarse graining. Firewall 4. No claiming emergence without specifying the coarse graining that produced it. Emergence requires declared loss. Firewall 5. No selection bias disguised as transformation. The method must be neutral with respect to the conclusion. Firewall 6. No entropy without coarse graining declaration. Entropy is meaningless without declared grouping. Firewall 7. No pretending coarse-grained results contain fine-scale information. Loss must be acknowledged. These protections ensure that coarse graining remains transparent. 23. Refusal conditions. We refuse to certify a coarse graining claim if the coarse graining procedure is undeclared, loss inventory is missing, preserved structure is unspecified, loss justification is absent, uncertainty change is hidden, replayability impact is ignored. Entropy is claimed without coarse graining declaration. Refusal here is not pedantry. It is protecting the honesty of scale transitions. Beyond science, coarse graining in life. Coarse graining is not only for science, it is for how we make sense of the world. In everyday life, we constantly coarse grain. We summarize experiences, average over details, form generalizations. A friend asks, "How was your trip?" We do not describe every moment. We coarse grain. It was wonderful. We saw amazing sights, ate great food, met interesting people. We lost details, the delayed flight, the minor argument, the uncomfortable bed. But for the purpose of sharing the experience, the coarse grained summary is appropriate. The danger comes when we forget we have coarse grained, when we mistake our summary for the full experience, when we think the average captures everything. In relationships, we coarse grain others. We form summaries. She is kind. He is reliable. These summaries are useful, but they lose detail, moments of unkindness, lapses in reliability. If we forget the loss, we may be surprised when the detail reappears. In self-understanding, we coarse grain ourselves. I am an optimistic person. This summary is useful, but it loses moments of pessimism, doubt, fear. If we forget the loss, we may be unprepared when those moments arise. Coarse graining is necessary, but it requires humility. We must remember what we have lost. A final image, the map and the territory. A map is a coarse-grained representation of a territory. It preserves some structure, roads, cities, boundaries. It discards others, individual trees, blades of grass, the texture of soil. The map is useful, it helps us navigate, but it is not the territory. If we mistake the map for the territory, we lose the richness of the actual place. Coarse graining is like map making. It creates useful representations at different scales, but it must declare what it leaves out. The honest map includes a legend. It tells us what is shown and what is omitted. Coarse graining requires a legend too. Closing insight. We began with comparability. From phi emerged distinction. From distinction emerged pattern. From pattern emerged identity, persistence, interaction, measurement, memory, modeling, prediction, learning, intervention, computation, information, publicness, scale. And now coarse graining. Coarse graining is how we move between scales without pretending nothing was lost. It is the bridge from micro to macro, from detail to summary, from individual to collective. It is necessary, but it requires honesty. Loss must be declared. We now move forward. With coarse graining understood, we can finally address what emerges at newest scales. Patterns that become visible only when we coarse grain. That is emergence. That is part 44. Always, peace be upon you.